Okay, everybody. In our previous video, in part one, we studied the concept of the uniqueness of basis representation. That was a very important concept. Again, this is section 4.5, of course. And now we're going to do two extremely important theorems. Remember, the title of this section is basis and dimension. And these next two theorems are going to help us uh, give a precise definition of what it means, a dimension, or it's going to help us give any kind of definition of dimension. But let's just go through the theorem one by one. So the first theorem says that if S is a set of vectors, notice there are n like November, there are n vectors in this set. And if this set is of n vectors is a basis for the vector space V, then what's going to happen is that any random set, any set I take of more than n vectors from this vector space V will always be linearly dependent, which means that if I have n vectors form a basis, then any set of more than n vectors will always be linearly dependent. That's really important. So let's just go through the proof. So first we're saying, let's just say that so S is our basis. Let's just say we have a set of vectors, S1, we'll call it S1, and it's a set of vectors, U1, U2, up to UM. And let's say this is more than the n vectors we had up here. So meaning that the number m is greater than the number n. In other words, that's Mike is greater than November. Now, we want to show, our goal is to show that this set S1 is linearly dependent. And in order to accomplish that goal, we have to find scalars. We're going to call them K1, K2, up to Km, M like Mike. And we have to find scalars to make this vector equation. K1U1 plus K2U2, with KMUM. And we have to show that it's possible to do this in a way where the k's are not all zeros, because if it's independent, then the k's would have to be all zeros. If it's possible to make at least one k non-zero, it's okay if they're all zero. At least one has to be, well, two, whatever. At least some have to be non-zero, and that's our goal. Now, we know that S, the original S, is the basis for the vector space. So that means every one of these vectors in S1, U1, U2, can be expressed as a linear combination of the original basis vectors, original S basis vectors. By the way, we're not making any claim about S1 that it's a basis. We're not making any such claim. We're just saying that S1 is a bunch of vectors, and it's more than I have in the basis. Anyway, we're gonna express U1 as a linear combination of the V vectors. That's from the basis. U2 is expressed as a linear combination. UM is expressed as a linear combination, so on and so forth. And now what we're gonna do is we're gonna substitute all of these. So we have U1 is some whole big expression, and we have a U1 up here. There's a U2 and then a U2 up there. So basically, U1 is this whole thing right here. C1 1V1 plus C2 1V2 plus CN 1V and da. So this whole yellow bunch of stuff is going to go into that U1 right there. And then this whole guy down here is going to go into the U2 over here. And this whole right side of the equation over here is going to go into the UM. Now that means, suppose what I want to do now is I want to sort of regroup everything. I want to find all the V1 vectors and the V1 vectors and the coefficients of those vectors. So since I'm multiplying U1 times K1, so the coefficient of V1 in my final in this big equation here is going to be K1 times C11. But here I'm multiplying K2 times and what's going to happen in this guy over here, I'm multiplying K2 times U2, which means K2 is going to multiply C12 of V1. So the coefficient of V1 in the second equation is going to be K2 times C12. And then if you go all the way down the line, the coefficient of V1 in the from the last guy is going to be Km times C1m. And that's all. And what's going to happen is that we're going to have a whole bunch of very long, coefficients, but I'm just going to call them D1, D2, Dn. But each D is, for example, the first D is C11, K1 plus C12, K2 plus C1m, Km. That's what the first one is. The second D2 is, same idea. Well, basically, here's the thing. We know that the VIs are linearly independent. How do we know that? Because it's a basis. Now, since it's linearly independent, that means the only way this equation here, say I did the substitution, I got this equation, but the only way this equation is ever going to happen is if each D is equal to 0. How do I know that? Because the V vectors are from the original basis and they're linearly independent. So since I could set all of these equal to 0, which is I'm going to set all these equations here, these guys right here, I'm going to set them all equal to 0. So what I get here is C11 K1 plus C12 K2 dot 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 plus C1m Km dot dot dot. Now the C's are all given. We established those up here. The variables here is really the K's, K1, K2, so on and so forth. Well, look at what we have here. How many equations do we have and how many variables do we have? We have M like Mike variables, and N like November equations. But we know that Mike is greater than November, which means we have more variables than equations. And everyone knows that if you have a homogeneous system where there's more variables than equations, we learned way back that this is always going to have non-trivial solutions. There's whenever we have a homogeneous system of equations, which has more variables than equations, then we know that there will be non-trivial solutions. Now, what does that mean? So if it's non-trivial, that means there are solutions where the K's are not all equal to 0. But don't forget, we started this whole thing with this guy right here, and we wanted to show that we could find K's which were, we needed to show that we could find K's which are not all 0. But from here, we see, so we've accomplished what we were trying to do. Remember, way up on top here, we were trying to find K's which are not all 0 that would make this equation true, make it equal to 0. And we see that there have to be K's that are not all 0, because in this system, in this last bottom system here, we have more variables and equations. So therefore, there have to be non-zero K's that make this work, which means the K's here are not all 0, which means that these U's indeed are linearly dependent. So all I really used about the U's, I don't know, what these vectors are. The only fact I really used here is the fact that there are more U's than V's, which is what we're trying to show. So we're trying to say that if I have any random set of vectors in the vector space, and which has more vectors than there are in the basis, then that set will be linearly dependent. So for example, let's say you have R3. We know that R3 does have a basis consisting of 3 vectors. We know that because that's the standard basis, 1, 0, 0, 0, 1, 0, and 0, 0, 1. We know that that's the standard basis. We know that there are 3 vectors in that basis. So this set here, which consists of 4 vectors, I don't even have to think about it. I know that this set here is linearly dependent. And that's what from theorem 4.10, the theorem we just proved. And let's say P3, we know that it has a basis consisting of 4 vectors. We've seen it already. 1, x, x squared, x cubed. So this set here, it's hard to see this, but you have to look at the commas. 1, 1 plus x, 1 minus x, 1 plus x squared, comma, 1 minus x plus x squared. So this is 1, 2, 3, 4, 5. This is already 5 vectors. So since it's 5 vectors, and we know that there's a basis of 4 vectors, without even thinking about it, working on it, without going through any lengths and no matrices, no dependent, nothing, to any work, we just automatically know that it must be linearly dependent. Now the next theorem is kind of fun, is kind of cool because uh, and this is really going to get us to that goal of defining the term, the concept of dimension. But it's fun. It's just I find it amusing that the next theorem, 411. Like, hey, what's the story? 411 information. If a vector space V has one basis with n vectors, then every basis for V has n vectors. And we're gonna, this is really gonna sort of be a result. We're gonna prove this using the theorem that we just proved a couple of minutes ago. And what I kind of chuckle when I see this is that the proof is much, much shorter. In fact, that's the whole proof right there. It's just a couple of lines and we're done. So what is the proof? So let's let S1 be a set of n like November vectors, and let's say that's a basis for V. And let's say that S2, which is a set of m like Mike, vectors, and that's a basis. Now I'm not saying which is more, but we have n vectors here, m vectors there. So we know that S1 is linearly, we know that S1 is a basis, and we know that S2 is linearly independent because it's also a basis. But the theorem that we just had before said that if S2 would have more vectors than S1, S1 is a basis. If S2 would have more vectors than S1 has, then it would be linearly dependent. But since it's not dependent, it's independent. It must be that this second set S2 must have less than or equal to as many vectors. So M, the number of vectors here, must be less than or equal to. It could be equal to it. It could be less than it, but it can't be more. Well, you could do the same argument in the flip side, because S2 is a basis and S1 is a linearly independent set. So from that, doing the argument just in the reverse direction, you get that n has to be less than or equal to m. Well, if Mike is less than or equal to November and November is less than or equal to Mike, the only way that's possible is if they're both equal to each other. Otherwise, how is that possible? So look how short that proof was. But it's going to help us, as I said, it's going to help us define this idea of dimension. Before we do that, let's just look at a couple of just examples here. Spanning sets and bases. So we want to explain why the following statement is true, or each one is true. The set S1, which is 3, 2, 1, 7, -1, 4, is not a basis for R3. How do I know that? Because we know that there's a basis. We know we've already shown the standard basis, which has 3 vectors. Therefore, every basis has 3 vectors. So S1 cannot possibly, since it only has 2 vectors, it cannot possibly be a basis for R3. Now, whether S1 is dependent or independent, we're not even discussing that. All I know is that it's not a basis. Now, by the way, since it's only 2 vectors, you can look, and one vector is not a multiple of the other vector. So we know that these 2 vectors we know that this set is linearly independent. It happens to be, but that's not what we're trying to prove. We're trying to just show that it's not a basis. Similarly, S2, which is x plus 2, x squared, x cubed minus 3, 3x plus 1, x was which is how many? It's 1, 2, 3, 4, 5 vectors. Well, again, 5 is greater than 4, so the S2 could also not be, must not be a vector, must not be a basis. This is really interesting. I find this is sort of an application, the RGB color model, and the 3 primary colors are red, green, and blue. And this is interesting to me. First of all, I actually, as a kid, I remember learning that the three primary colors were red, blue, and yellow. And here we're saying it's red, blue, and green. So what I learned was that if you're drawing uh, colors like on paper, then then yellow is one of the primary colors. But when you're looking at colored light, for some reason green is the primary color, not yellow. Which and you see that the intersection of green and red gives you yellow, which is kind of interesting. So there's a difference between light shining and making color, or crayons, making color, or whatever, paint, or whatever you do. Um, anyway, using applications of linear algebra, we can model these color things. So it's kind of interesting application, interesting and useful. Now, we can finally define the dimension of a vector space. And I think I'm going to make a separate video on this. So we're going to make that part 3. I'll see you guys in part 3.